Welcome back to Science Click. Today, the mathematics of general relativity, part 6, energy fluxes. Our universe consists of a fabric, space-time, on which we place content, stars, mass, energy. At first glance, the content of the universe seems very diverse. There are stars, planets, interstellar gas clouds, or even living beings like us. Yet all this diversity can be summarized with a single concept: movements of energy. Energy is an abstract notion which indicates the presence of disturbances in the universe. In particular, it can arise from mass. Mass contains energy according to the formula E equals mc squared. But other factors also contribute to the energy content of the universe, such as the electromagnetic field, or even dark energy, which is known to have negative pressure. In all its forms, energy moves through space-time similarly to a fluid. The presence of an apple, for example, can be modelled as a flow of energy. To describe it, let's consider a point on the trajectory. From this point, the motion of the energy can be transferred in different directions. On a two-dimensional sheet, energy can pass through 4 different sides, 2 along each coordinate. However, the situation is symmetrical. If energy enters the point from one side, it must leave through the opposite side. Thus, only 2 surfaces are needed to fully describe the fluxes of energy. If the apple remains motionless through space, its energy moves only through time. Thus, only the surface associated with time will be crossed by the flow. And if the apple is moving through space, then both the time and space surfaces will be crossed. For each surface, let's represent the flux of motion which passes through it by a vector. Depending on the behavior of energy, like a sort of fluid, these vectors can vary. Breaking them down into their components, we can create a table which contains these 2 vectors. This tensor describes how momentum is transferred along the different coordinates. We denote it capital T and call it the energy momentum tensor. In this tensor, the first component measures the amount of energy traveling through time. This component indicates how much energy crosses the point, moving towards the future. It's more commonly called the energy density. It gets greater when more energy passes through the point. The next 2 components are equal. Both measure how much energy travels through space over time. This is momentum, transport of spatial motion over time. This value is greater when the energy moves faster through space. These components are commonly called momentum density. Finally, the last component in the table measures how much motion through space is transmitted through space. This is more difficult to interpret because we must find a meaning to this transfer of motion through space. This is a tendency that energy has to push in one direction. It is commonly called pressure. In this 2-dimensional example, the table contains only 4 components, 2 of which are identical. But in our 4-dimensional universe, this tensor actually contains 16 components. It contains the energy density, the amount of energy that progresses towards the future, the momentum density, which is this time broken down into 3 components for each direction through space. Pressure, which is also expressed along the 3 directions, but also a bunch of other terms which correspond to viscosity. Viscosity is the tendency that energy has to transfer its motion to its surroundings. It's important to understand that the components of these fluxes of motion depend on the coordinates that we choose. If we change coordinates, a motionless energy can become a moving energy. In other words, motion is relative. It depends on the point of view from which it is observed. To illustrate this energy momentum tensor, we will look at 2 standard examples. The first example is that of an empty spacetime. When we calculate it at a point which is crossed by no energy, the energy momentum tensor is 0. All its components vanish. This very simple case is fundamental because it is the one that we will use most often. Indeed, when we want to describe the motion of a small object through space-time, for example a satellite around Earth, or an apple near a black hole, we can neglect the energy of this small object, which is very weak compared to that of the central body. We can consider that the object is located in empty space, and the energy momentum tensor vanishes. The second concrete example is the case in which we are interested in the inside of a body. For example, we may want to describe how an object behaves inside the sun. In this case, even if we neglect the mass of the small object, it is still not in a vacuum, because we have to account for the matter that makes up the sun. In such a case, the energy momentum tensor is not 0. If we consider that the sun is formed by a perfect fluid, without viscosity, and at equilibrium, then the tensor contains only an energy density related to the mass of the sun, and a pressure directed outwards, which prevents it from collapsing in on itself.